Good morning, grade 12s. I'm making a little video for you to go through today's class, which is about approximate solutions. I'll try and keep it quite short because it's based on some maths that we already know about. So by all means, take time to pause the video where you need to read through things or to practice things on your own. So you can have a read of this section at the top. All of the coupled systems we've been looking at, the differential equations have been linear ones. Obviously, as the equations become more complicated, the techniques we've used so far are not going to work anymore. The way that we're going to look at trying to solve these is by using a numerical method, and it's one that we actually used in the integral calculus unit. It was Euler's method. So this here is from our integral calculus unit, and it was if we had a differential equation with y and x that we couldn't solve using separating the variable or an algebraic technique. So we looked at using this. Obviously, with our coupled systems, we're going to have two differential equations. That's what we've had so far. And the dx by dt could be in terms of x or y or both. The same with dy by dt. So rather than just having an equation for the next x value and an equation for the next y value, we're going to have a third equation, which is for the t value. So if you think about the solutions we've been getting, they've been x and y in terms of t. So this is what we're going to be looking at using today. So this is for coupled systems. And this is in the formula guide. It's in topic 5, right near the bottom. We'll look at how we use it now. So we'll talk about the workings you need to show, because remember, from integral calculus, when we do Euler's method, most of it's on the calculator. So there's not a lot of workings we need to show, but we need to make sure we do those. So here's the example we'll do then. Use the Euler method to find the values of x and y when t equals 1 and t equals 2 for the system of differential equations below. Use a step length of h equals 0.1. This is actually an example of one we could solve with the methods we've been looking at. We could, set up the matrix, find the eigenvalues, find the eigenvectors, and get a particular solution because we've also been given the starting values there. But we can also use Euler's method. And after we've done that, we're going to make a comparison between the results we got using Euler's method and the exact ones. Okay, so I'm going to need my formulae, so I'll try and keep those on the page as well. So to get the next x value, so these are my workings out. So that n plus 1 is the next x value. I take the x value I know, and then I add on the step length, which in this question is 0.1, and then I multiply it by the slope function I've got, the dx by dt function. So it's 3 lots of xn minus 4 lots of yn. Okay, I'm going to put this into U1 on the sequence app, and I know my initial value, x0, is 4. Okay, and then we go through and we do the same thing for yn plus 1. So yn plus 1 is the previous y value plus 0.1 times, okay, I'm just reading off dx by dt, it's xn minus 2yn. I'm going to put this into U2 on the sequence app, and y0 is negative 2. And then finally, we need a function that kind of keeps our time variable ticking over, and that is going at 0.1. I'm going to put this in U3, and the initial time is 0. Okay, so I've got all that. My next job is to put this into the calculator app. So I'm looking at the sequence app. I've got a load of stuff in here from probably when we were last doing integral calculus. Okay, so let's start. U1 I said was going to be Oh, I need to make sure this is n plus k, so it looks more like our formula guide. So it was xn plus 0.1 times, and I've forgotten this, 3xn minus 4yn, so 3xn. xn is going to be found in the u1, minus 4yn, so minus 4 times, and then y I'm putting in u2. And I wrote that down in my workings as a reminder to myself. Okay, I think the initial value is 4, so I should put that here. U1 0 is 4. I can't check this yet because I don't really have anything for U2 yet, so it's not very happy there. Okay, I'm going to do the same here. So I take yn plus 0.1 times xn minus 2yn. So xn, x is in U1. xn minus 2 times yn. Okay, and what was this starting value? The starting value was negative 2. xn minus 2yn. Yep, I got that right, and that's negative 2. And then my last one is my time function. So this started out at 0, and it is u3 plus 0.1 times, oh, just plus 0.1, isn't it? Hang on, sorry. It's u3 of n, so like the previous time value, plus 0.1. Okay, they're now all checked now. I'm able to check that first one, which is a good sign. And then I go to my table, and in U1 I've got the x values, in U2 I've got the y values, and in U3 I've got the time values, which looks a bit strange. See how there's that, I don't have anything there. I'm just going to go back. I think maybe I set something up incorrectly. So, oh, okay. So you see I've got start n0 for U1, start n0 for U2, start n1. I just need to make sure they all match up. It doesn't matter so much what value it is, just make sure they're all the same. So now when I go back to the table, yeah, there we go. So just to explain that again, it was at 1. So you'll see it started with that first 0 value at 1. And that's not right. Time is 0 when x is 4 and y is negative 2. So that's a good thing to be checking. Okay, so the question was, find the values of x and y when t equals 1. So let's do that. Okay, when t equals 1, x equals 48.1, y equals 11.0. And then I do the same when t equals 2. So I'm going to scroll down, 306, and y equals 76.2. Okay, so that is using Euler's method. Obviously, the smaller the step length, the more accurate our results are going to be. But obviously, it requires more time for the calculator to do it, and it requires us to scroll through more. But yeah, it will give us some more accurate results. So as I said at the start of this example, this is one we could have done using our matrix and eigenvalue method. And you can see in part B that they've given us the exact solution. So what we could do is we could find the percentage error in the values we found. We'll just do it for one of them because the process is the same. So when t equals 2, let's do when t equals 1 actually. I'm just going to substitute t equals 1 into this equation and find out the values of x and y. So 2e to the 2 times 4, 2 times e to the 2 times 4. I'm doing the top line at the moment, minus 4 times e to the negative 1 times 1. Okay. What's wrong? Oh, I missed out this multiplication sign. Okay, so the calculator gives me 57.6 for the x value. And then for the y, I'm going to do something similar. there's a 1 at the bottom there, and there's a 1. Okay, so the y value is 13.3. Okay, so comparing that to the answers I got 48.1 for x, now I've got 57.6. I got 11.0 for y, and I've got 13.3 for the y this time round. This is obviously my more accurate solution because it's using the exact solution to the differential equations, and then I've just rounded them to 3 significant figures. This one over here, I am getting an approximate solution, so this is less accurate. If, as I said, if I made the h, the step value, smaller, I should find I get a more accurate solution. And if you want to try doing that, change the h in all 3 equations to 0.01, and you should find you're getting a more accurate solution. And of course, we could take these and we could find out the percentage error. So to find the percentage error, we do the difference. So I'll just do the percentage error for the x values. So I'm going to find the difference, 57.6 minus 48.1. We divide it by the exact solution, the exact answer, and we times it by 100. So this is our percentage error. Okay, and I'll take that, minus 48.1, divided by the exact one, times 100. So there we go, we've got a percentage error of 16.6%. Okay, it's going to be the same process for finding the percentage error for y, and obviously if we did time equals 2, it's all the same process again. So, in terms of workings out, you do need to put in this information. These are our workings. And you'll notice that instead of just writing x, I'm writing xn and yn plus 1. So I'm trying to use the notation that I should be. There's very little workings out other than that for these questions. So, yeah, that's something we need to do. On the next page, there's 2 sets of calculator instructions. We're using the lower one, the one that makes it look more like our formula guide. You will see people using the one above, but that's not what we did for the integral calculus unit, so we should stick with the same process. Okay, do practice this. You'll remember you have to be quite careful when you're putting things into the calculator. It's like one little mistake can throw everything out. So yeah, do take care with when you're putting this into the calculator. Okay, I will hopefully see you all in our next lesson. Bye-bye.